we're now going to take the idea of domination one step further. Or really, we're going to take it many steps further. Look at this game. Neither A nor B is a dominant strategy for player 1. So which one should player 1 play? Well, it's going to depend on player 1's beliefs. Let's suppose his beliefs are theta 2, which is represented by P, Q, and 1 minus P minus Q. P is the probability of playing X, Q is the probability that Y is played, and the remaining probability is the probability that Z is played. What's the payoff to player 1 from playing A if these are his beliefs? So U1 of A given theta 2 is, with probability P, player 2 will play X, and player 1 will get payoff of 3. With probability Q, player 2 will play Y, and player 1 will get 0. And with probability 1 minus P minus Q, player 2 will play Z, and player 1 will get 0. So that's just 3 times P. Player 1's payoff from playing B in expectation, given his belief theta 2, is with probability P, player 2 plays X, and player 1 gets 0. With probability Q, player 1 gets 3, because player 2 will play Y. And with probability 1 minus P minus Q, player 2 will play Z, and that will result in a payoff of 1 for player 1. Adding that up, we get 1 minus P plus 2Q. So when is A a better option? The expected utility from A is at least as high as the expected utility from B, if and only if 3P is at least as big as 1 minus P plus 2Q. We can rewrite that in a simpler way as P is at least a quarter plus Q over 2. So what's the best response? Again, if P is strictly bigger than a quarter plus Q over 2, then A is strictly better. If P is less than a quarter plus Q over 2, then B is strictly better. And if P is exactly equal to quarter plus Q over 2, then A and B are equally good. So the best response for player 1 to their beliefs is just A if P is bigger than a quarter plus Q over 2. Just B if P is smaller than a quarter plus Q over 2. And both A and B if P is exactly equal to a quarter plus Q over 2. This is just a mechanical calculation of the best response. We still need to know where the belief comes from. Where does theta 2 come from? What should theta 2 be? Well, to get theta 2, one would have to put herself in player 2's shoes. But if she put herself in player 2's shoes, what she's going to realize is that Y dominates X. So player 1 can conclude that there's no way player 2 is going to play X. So P has to equal 0. From our best response function, we know that this means that player 1 is not going to play A. Again, by common knowledge of rationality, player 2 can put herself in player 1's shoes and figure out that player 1 would go through this line of reasoning. This is because player 2 knows that player 1 is rational, and player 2 knows that player 1 knows that player 2 is rational. So player 2 knows that player 1 is going to deduce that player 2 is not going to play X, and is therefore not going to play A herself, and therefore player 2 can figure out that player 1 is going to play B because she's not going to play A, and that means that player 2 should play Z, because Z gives her a better payoff of 2 than 1 when player 1 is going to play B. The process we went through here is to figure out that player 1 is going to think in his head that because player 2 is rational, player 2 is not going to play X, so we can disregard that entire column. And because we've disregarded that column, player 1 is going to think to themselves, well, since we're not playing that column, I can just look at the remaining game. But now I see that B dominates A, so I can decide I'm not going to play A because A is dominated by B. Then 2 is going to, in 2's head, figure out that 1 is going to go through that reasoning, and so 2 is going to know that the game is just between these two cells. 1 is definitely going to play B, and 2 just has a choice between Y and Z. But of course, Z then dominates Y, so player 2 would never play Y. And that leaves us with just one profile of strategies. This process is what we call iterated removal of dominated strategies. Some people use the word elimination, so iterated elimination of dominated strategies, but they would mean the same thing. So the way this works is you start with the set, let's call it R0, as all possible profiles of strategies. And step 1 is to delete all dominated strategies in R0. You keep going, and in step K, you look at the game where all you've got left are the strategies in RK-1, so the ones that survived from the previous step, and you say, okay, in this remaining game, do we have any dominated strategies? If you do, you delete those, and that gives you a new set, RK. Now you continue this until you don't delete any more strategies. Call the remaining strategies the set R. So R consists of all those strategies that survive iterated removal of dominated strategies. It's of course going to be a subset of the set of all strategies. In the example we saw above, we started with 2 strategies for player 1, 3 strategies for player 2, and we ended up just with 1 strategy for each. This set R is often called the rationalizable set of strategies. The reason it's called this is because if you remember about the 2-player version of the equivalence result we saw earlier, these are the strategies that could be a best response to something because we have the equivalence of being undominated and being a best response. So these are the strategies that could be supported as best responses to best responses to best responses to best responses. It's important to notice here that common knowledge of rationality is critical if you want to perform this exercise of iterated removal. If rationality wasn't common knowledge, for example, if I knew you were rational, but I didn't know that you know that I know that you're rational, and similarly, you know that I'm rational, but you don't know whether I know that you know that I'm rational, then we can only do 1 round each of these. We can't keep going ad infinitum. To be able to keep going for infinitely many rounds potentially, or an unspecified number of rounds, since these are finite games, this iterated removal would end in some finite number of rounds. But in order to be able to keep going arbitrarily long, you need infinite depth of reasoning, and you need common knowledge of rationality. So what if we only had some finite depth of reasoning? So I can put myself in your shoes, and in putting myself in your shoes, I can put myself in your shoes, putting yourself in my shoes, and I can put myself in your shoes, putting yourself in my shoes, putting myself in your shoes, and so forth. But I can only go some depth. There's actually experimental evidence that people can't go infinitely deep in this type of reasoning. Most people only go to a certain depth. So there are these models called level K models in behavioral economics, which allow us to explain the behavior that's caused by people not having infinite depths of reasoning.